through space with a tiny sun.
Hey, I'm FTFE, welcome back to the channel that ties stupidity to the train tracks of knowledge. Tonight we have a debate with, well, it's more of a discussion really, with a concave earther, which is the third concave earther I've had on the channel. One of the concave earthers that I had on the channel, with the previous one, was a guy who called himself Lord Stephen Christ Mercury, who actually contacted me today out of the blue to say that he is no longer a concave earther and denounces Lord Stephen Christ, and believes that the heliocentric model is correct. And he asked me to remove the video that I had of him, so that is now down, because he didn't want anyone finding his arguments and using those to to push concave Earth. So yeah, he is no longer Lord Stephen Christ Mercury. He said he'd be watching tonight, so hi if you're there. I was quite happy with that. But anyway, on to tonight. With me tonight, I have a concave earther who is called Zenith Atlas. Welcome to the show. How you doing?
How are you? Thanks for having me.
I'm well. Thank you for joining me. Yeah. So, would you like to just take a couple of minutes, introduce yourself to the people, and tell them why you hold the position that you do?
Sure. My name is Joshua James Bolliero, and I got into considering alternative cosmologies in 2015 with flat Earth, and I gave that its fair shot. And I actually did believe the Earth was flat for a while, and I no longer hold that position because it just doesn't have as much substance as I initially thought. And so upon further review, I realized that there obviously is curvature, and we do live in or on a spherical world, just based on simple A to B distances and plotting out this, all the cities of the world. And so I hold the position that the Earth is most likely stationary while the gravitational forces are rotating. And that we live on the inside. The curvature goes up, not as opposed to down. And optically, that's going to be up to semantics, and we'll discuss that later here today. But so I have moved through several different cosmological models, and where I sit right now is that the Earth is spherical, stationary, and concave. And of course, science doesn't ever prove anything, so that's always why we're having these conversations and sharing new information with each other, so that we can, look at the predictions and observations and learn from that. So this is all part of our journey, and I'm thankful to be a part of it. And I hope everyone can learn, including myself.
Okay, so you're open to learning more about the shape of the Earth and exactly where we live. Is there any hints that you think it might be, convex rather than concave, or are you pretty set on concave?
I'm not. Well, that would be kind of dogmatic of me and not very scientific to be set on something. The preponderance of evidence does lead me to believe it's concave, while the best piece of convex evidence would be the spherical excess. And while I do understand that that's based on averages and still based on optics, so that's subject to human error, I do acknowledge and validate at least the claim, which at least is measurements and is evidence that adds to confidence.
Okay. So do you hold the position that all space agencies are lying to us?
Yes.
Is any of what they say true or correct, or is it just
Yes.
all a complete fabrication? Right. Okay.
Yeah. Well, of course. Yeah. If you're gonna lie, you have to take a lot of time.
Okay. Right. We can get into that. But something you said there interests me. The talking about spherical excess. Obviously, surveyors use it when doing their job, and it was, I think, a good example of spherical excess that can kind of demonstrate that it can be more than just optics is when we're talking about the construction of the LIGO, the massive interferometer, because they had to take spherical excess into account when building that, because the 1 kilometer long arms are so long that if the laser was to be completely straight, then at one point it would be further away from the center of the Earth than the other. And they had to take that into account, and actually at the end of the arms they had to build a lot of, I think a meter or something of cement underneath so that it was straight, and it was along a waterway as well, so it was level, because if we use the term level to mean with the curve of the Earth either way, then it was level, but the laser needed to be straight rather than level, so they had to take that into account. So why did that show convex rather than concave?
Well, it like I said, it does have to do with optics, and if we're talking about a laser beam, excuse me, which is a light is subject to bending towards the more dense medium. So now because the whole premise of the concave Earth model is that things are inverted, and our view of the sky is inverted, our view of everything is inverted, then that means we have to consider that when we're looking and we're seeing a laser, what is straight? What is, is that laser bending upwards? Is it really bending downwards? Is it bending one way while we're thinking it's bending another way? These are all things that have to do with how our eyes see, and so it's really optically.
If a laser was to go through a vacuum, would it be straight then, or would it still bend? Because you said it's obviously to do with the density of the medium, which I agree with. We can get into the exact of that afterwards. But if a laser was to go through a vacuum, would it go straight?
Well, that would all depend on your definition of vacuum and the amount of torque that you're talking about, because there's different vacuum chambers that can provide different amounts of torque.
Yeah,
and of course, a near perfect vacuum is almost impossible to replicate.
Yeah.
So my answer is I don't know.
10 to the negative 11 torque to 10 to the negative 17 torque. They're practically the same. They still have very, very, very little in, so little that it wouldn't affect the direction of light. Obviously, LIGO is within a vacuum. So as far as I'm concerned, that means that the light wouldn't refract, it wouldn't bend, which shows that there is a convexity, because if it's straight, then it's leaving from the center of the Earth, and that's what we see in LIGO.
But what you're saying is that light doesn't bend in the vacuum.
No, because there's no medium.
But where this laser experiment, where we're conducting these experiments, is not in a vacuum. It is in an atmosphere that, at ground level, within a mile from the surface of the Earth. So we do have, we are going to have bending light, because the air is a fluid, essentially. And any fluid is going to bend light, including air. And so that laser beam is subject to bending, because we don't, even according to the heliocentric model, where humans reside is not vacuum. There's 62 miles until the Kármán line, and we live in a reality where we have pressure and all these things. Lasers will bend, and so that's going to take away from the confidence for any model, whether it be concave or convex. I could present laser experiments that show concavity, and because light's bending, now my arguments have less weight as well, not just yours. Yeah, so that's something that we all have to consider.
As Digital Demonic Davros in the chat points out, it also has helium cooled magnets to keep the laser straight. Everything about the LIGO is designed to make sure that the laser doesn't bend. That it's a vacuum. It's everything about it is designed so that there is no medium, so that the light won't bend, so that it can detect the minute changes in space-time due to gravitational waves.
Okay.
So if
How
is
how
designed
how
to
but
stay straight.
but if that's being conducted in a vacuum, how does that apply to the natural world, which is not a vacuum?
That's the whole point. You don't have conditions naturally to have a completely straight laser, but to be able to do what it does, it needs to have a straight laser. It needs to have a
Right.
complete straight line of sight on the two arms. So it has to make sure that it is straight. You know, that's literally the purpose of it, so that it can detect the minute changes.
Oh, you broke up there for a little second. I
All
didn't
right,
hear.
sorry.
Could you repeat that again? I'm sorry.
Yeah, I'm just saying that is the point, that there isn't conditions in the natural world that you can do this experiment. The whole point of the experiment is that you have to change the conditions so that it is right, and that's how they know the lasers are completely straight.
In a vacuum.
Yeah, there's no medium in a
Okay.
vacuum, so there's no reason for the
Right.
light to bend.
So there's nothing bending the light.
Yeah,
So but how does that apply? How can we then use that to determine the shape of the Earth if
because
we would have to shine a laser, say, over water, which is not in a vacuum? How does
well, I mean, I think everyone's heard me say that I think laser experiments over water are kind of inconclusive in any way, because we will agree that the density of a medium refracts the light, so there's going to be a bending of the light. So that's why I don't think that they're worth anything, and that's why in LIGO they have to make sure that the light doesn't bend, so that it is completely straight, so that they can tell what's happening. And then how you can use that to test against the real world is to see that if it then at one end has fallen away from the Earth, raised above the Earth, that means that the Earth is convex, not concave. If it was encroaching on where the laser was supposed to be, then that would mean it was concave. So, I mean, I think LIGO is an extremely good demonstration of the shape of the Earth.
Okay, I guess I'll have to look into that one a little bit more to see exactly what it is. I mean, how? Yeah, I just don't know the experiment, so I guess I just have lots of questions about it because I didn't look at it.
I mean, the main point of LIGO is
I'm
the
failing
laser
to make
has
the
be
connection
straight.
on.
So if you can then use that as a reference, if you know that that is actually straight, there is no medium bending it, then you can use that as a reference as to what the real shape of the Earth is.
I guess I until I look at the experiment, I just don't know how they did that.
Okay.
How, they did they actually create a scenario of a vacuum over a body of water and use a laser? Like what?
No, it's just that
What?
the whole point of
Once you
LIGO is that
determine
it's a contained system, and
right,
if that is, we can use that as a reference as to what truly is straight, and then if
right,
the Earth curves based on that.
Right, how is that used as a reference?
Because if
Because
that
I
is
mean,
straight, then we know what the shape of the Earth is based on that, because you can use it as a reference to it. So if it would create a tangent.
Well, what?
So,
What? Okay, so the LIGO experiment deduces that in a vacuum, the laser won't bend. Light won't bend in a vacuum.
That's not the purpose of the experiment. The purpose of the experiment is to use the fact that the laser is straight, and knowing that based on the curvature of space-time and how much that would make the laser deflect.
Okay, so they used a laser in a vacuum. How big was this vacuum?
It's 1 kilometer long, two large 1 kilometer long. Let me get up a picture
Okay,
of it.
all right. So that gives me a better understanding. I didn't know if they're just in a little chamber. So they had 2 kilometers of straight laser sight.
Yeah.
Is what you're saying. Okay.
Let me
And
just put this
2
up
kilometers might be enough to determine. So they were they in a facility? I mean.
Yeah. Right. Sorry. One sec.
If they had a concrete floor or something, the flat earthers will say,
this
is
one of the arms.
Okay.
I'll get a better picture of it for you. Right, so that's LIGO.
Okay.
So each of those arms are a kilometer long, and they've got a laser
So
in.
this entire stretch is a vacuum.
Yeah, and just down the side here, there's actually a river or a stream running alongside it. So you know that it's level compared to what is level, and these have to be completely straight so that they can detect.
So the laser, so this straight laser is going to tell them whether there's curvature based on, you know, relative to from the laser to the floor.
Yeah. And so when they were constructing
if it's a man-made floor,
yeah. But the point is, when
what
they
is
were
that really
constructing
proving?
this, they at this end, they didn't have anything underneath the tube. Right at the other end, they had to have like a meter of cement to, you know, keep it off the ground. And that shows what the shape of the Earth is, that it actually fell away by nearly a meter at the other end.
And they were able to prove that their laser was level.
Well, straight, not level.
Ah, all right. Well, I mean, straight but not level. What does that actually mean? You know.
Well,
because we know level can work on
the level.
Semantics level can work on all three models. No.
Yeah. Well, okay. Well, let's stick with the definition of
parallel
level as meaning
parallel with the Earth.
Yeah, perpendicular to the curve of the Earth. So,
right.
I mean, the Webster's dictionary defines it as conforming to the curvature of the liquid parts of Earth's surface. So, whatever curve the Earth has, be it convex or concave, that is level. If we're talking about,
I'd say it.
Yeah. So to be straight would be deviating from level at one end, which this does, showing that the laser is completely straight and is not level with the Earth. Right.
Straight would only equal level on a flat Earth because
exactly.
Right. I got you. All right. So that's what you mean by straight is not following curvature of Earth, up or down.
It would create a tangent to. Let me go back.
It would create a tangent away from Earth on a convex Earth, and it would create a tangent towards Earth inside a concave.
So it's, it would be like that. It would be getting further away from Earth as it goes up.
So what you're saying is they level.
Sorry, you dropped out for just a second there. Repeat that.
So what you're saying is they had to build up, or they had to add to a convex Earth in order to get level, because straight wasn't.
Yes, exactly.
Straight was deviating away from the Earth.
Yeah, absolutely.
Okay.
So I think that is a really good demonstration of the shape of the Earth. The fact that they had to physically make sure that one end was higher away from the surface than the other.
Yeah. So I'll look into that a little bit more. What I saw was screenshots. I'll have to look for footage where they're going to have. I mean, with an experiment that complex, there's going to have to be lots of footage proving this, proving the camera was level, proving this, proving that, proving all these different claims. So I guess I'll have to go through that.
Yep, it's definitely a good one. Shields versus Shields says, on land, what a dim-dim. No, as I said, it was actually right next to a stream showing what level is. So, right, so what would you say is the biggest evidence, the strongest evidence that you've got to say that the Earth is concave?
That's a tough one because concave Earth is so many different small pieces put together. I would have to say we'd have to start with what's observable. I can observe upwards curvature. I can observe, when I say observe, I'm talking about I put a zoom camera, take it off the tripod, I put it low to the water, and I skim the water with zoom. And if you're going to do that, that should give you an indication on whether water is curving up, curving down, staying flat. And what I've come to understand is that the water, I mean, horizontally, yeah, of course you're going to have a flat horizon regardless of the shape of the Earth because a human is so small compared to the Earth. Horizontally, it's going to look flat no matter what. You're talking about a 6-foot tall person versus an 8,000 mile Earth.
Yeah.
But looking outwards, when I zoom out, when I look outwards, it never looks flat. In fact, most of the time it looks convex. Some of the time it looks concave. Now, the argument for refraction is that when you have more atmospheric conditions, we've all heard Tom Coombs say this, right? What you're seeing is a mirage. And then he goes on to explain refraction and how light will bend so that you can, on a convex Earth, you can see something over the horizon. Your line of sight is lifted, if you will. The refraction will lift lift distant objects so that you can see them at great distances. This is our explanation for why we can see Chicago from across Lake Michigan. So they tell us that more refraction will increase our visibility range because the refraction is raising these, upwards refraction, raising these objects. What I've found is that more refraction, and what's actually logical, what actually makes sense is that when there's more refraction, more atmospheric conditions, more lensing, looming, atmospheric magnification, stuff like that, when these effects are stronger because the air is more dense or more humid or what have you, that reduces, not adds to our viewability range. And so, like Steve says, I think it's an illegal argument to say that refraction will allow us to see further. I noticed that when the atmosphere is clearer and we have less particulates in the air, and the atmospheric distortion is at a minimum, that's when I'm able to see far. When things are less distorted from the truth, when I can see far, that's when it appears concave. The footage that I have is from a lake that is kind of a gem. It's a lake big enough but small enough. It's got to be small enough. The oceans aren't really great for P900 because you get the waves and tides and currents and all that stuff. That just ruins people's arguments. But with fresh water, which is less than that, it'll actually bend less. Salt water will bend more. Having a shoreline that's far enough away where you can do the math and show that the boats actually are in the dip. There's enough distance there where the dip is big enough to fit a whole boat in the dip. Having an opposite shoreline to match up with the boats is essential. Having it far away enough is important too, but having it close enough to see is important. And so that's why Lake St. Clair in Michigan is a gem, because most of the time I can't see the opposite shoreline, a certain portion of the shoreline, a certain portion that I look across all the time. Most of the time it's not there to see. And so I'm left up with no opposite shoreline, so my footage is really kind of moot. But when I can see far and visibility is clear and it's all blurry, it's crystal clear, it's obvious that the water is you can clearly see. And my camera altitude destroys that flat Earth hallway perspective argument, because on flat water, if my camera altitude is only 5 inches and I'm looking over a fishing boat that's 2 to 3 feet tall and there's men standing on it fishing, which means their heads are about 8 feet above the water, that means that on flat water, I have to be looking upward from 5 inches to see over the men. And on flat Earth perspective land, I would have my viewing angle on a flat Earth. The horizon will never rise to eye level on flat Earth. So on a flat Earth, if you're standing up, every viewing angle, no matter what horizon you have, it's always going to be a downwards hypotenuse, a downward angle. And so from 5-inch altitude, if I'm trying to look over 7 or 8 foot tall men, my viewing angle must be upwards. And if I'm seeing another boat above their heads, and then an opposite shoreline even above that, it indicates that there's concavity, and the further you can see, the further objects are, the more elevated they are off in the distance. And so my observations disprove. Now, even if the Earth were convex,
Oh, you dropped out a sec there.
the truth about refraction, I think it's
Okay.
inverted
Right.
because the curvature. I could be wrong about that.
The thing is that we know for sure that a more dense medium refracts light downwards. I mean, that's something that is easily demonstratable.
Well, we know that light refracts toward the more dense medium. If we assume that Earth is the more dense medium because the only thing up is sky and there's nothing
when
there.
we're talking about the more dense medium, we're talking about the air, and the fact that there is, the closer to the water, the denser the air is. The colder, the denser the air is, and that's how the way you actually want to calculate it is you talk about a coefficient of refraction, which is all to do with lapse rate, which is the change in temperature over distance, right? And you can quite easily calculate the coefficient of refraction, and if you have a coefficient of refraction of like 2 or anything more, then you're going to see for a long time. But it shows when you calculate that it shows that the light is bending down in the more dense the medium gets. So the denser, the more it gets. The refraction is a gradient as well. So I mean, standard refractive conditions only has to bend light 0.5% to bring something up for you to see pretty much as far as you want. And we know that light bends down into a more dense medium. So this is obviously the glass is more dense than the air around it. As the light enters it, the light bends down. So if that was the light you were seeing, it would look like what you were seeing was lifted up higher, even though the light's bending down, because you are seeing what the light has bent down to. So we know for a fact that is how light works, that it will bend down the denser the medium gets.
Right. So in the concave Earth model, light is both bending down and up. So at short range, the more refraction you have, I think the more refraction you have, it is going to bend things downwards, which is why I say that most of the time I go to get footage, the water appears convex, and I think it's because there's more refraction. It's knocking things down.
You're right, because the closer you are to the water, the more refraction you're going to have, because that's where the denser air is.
Right, it's knocking it down because it's initially up, is my point. It wouldn't be knocking it down. If it was already over the curve, it wouldn't need to knock it. That's what I'm saying. Refraction
it doesn't knock it down. It literally lifts the image up so that you can see further around the curve.
That's what I'm saying. That's what we're taught.
If you are closer to the water, that's where reality. If you're closer to the water, that's where the most refraction will happen. So it can quite easily make it look concave. But that's just because it is lifting up the perceived image so much.
I understand what the arguments taught are. What I'm saying is that personally, myself, I've disproven that, because I know that more refraction will knock things down, not lift them up, like Tom Coombs says. Refraction won't bring things back up over the curve.
But that's exactly what it does. If the light is bending down, which it does as it gets towards the more dense medium, then it will allow you to see further. What
a faulty presupposition is that scientists have assumed that downward is the more dense medium. In the concave Earth model,
because that's when we're talking about the medium, what we're talking about is the gradient of the air. We're not talking about the Earth being more dense. Light isn't just naturally bending down towards the more dense thing. It's as it goes through a more dense medium, meaning the atmosphere. And the lower, the closer to the water that you are, the denser the atmosphere is. So we know that
Right.
down
Okay. So
is where it's more dense, meaning that that will bend the light down.
okay. So leave what's on your screen there for a second. This is perfect. This is exactly my point. Okay. You see how refraction bend light downwards toward the colder region, towards the cold water. I
Yes.
agree that if you zoom across the water, your view is going to be bent downwards. So you see the two straight dotted lines pointing up to the superior mirage.
Yes.
Okay, so
So
what
but
I'm
that's, I
saying
mean, looming is what you can call that. It's what allowed the image of Chicago skyline to be seen, because it was
right,
raising the image up high enough beyond, above the horizon so that they could see it. And what
right, and
that
what
demonstrates
I'm
is
saying is
that
I
as the denser medium, meaning the atmosphere, gets more and more dense, the closer to the water it gets, the more it will bend the light down, meaning you can see
right.
further over the curve.
But if it bent your line of sight down towards the water, that means more refraction would reduce your visibility because it's being bent down more. The more it bends, the shorter you're going to see.
Well, no,
You see what
because
I'm
it's
saying?
it's bending it around the curve of the Earth. So obviously, when we say the horizon, we're talking about the physical obstruction of where the Earth
Right.
starts to curve away from us. Okay, and everything beyond that physical horizon we can't see because it's blocked by the curve of the Earth. But if light is bending around that curve, it will allow us to see what is over that curve
Right.
rather than just straight
Right.
up in the air.
I understand the argument. What I'm saying is that the argument is simply how much time have you spent at water filming? First of all, because I just
Quite a
don't
lot. I
know.
was in the
So
Navy for a long time.
okay. So have you ever taken a zoom camera and put it low to the water and zoomed across? Because
No, I've
what
not
I'm
done that
saying is
personally, but I have watched a lot of your footage, and
okay.
you're right. And because it's that is where the densest air is. That's where you're going to get the most refraction, because the coefficient of refraction,
Right. I agree.
the lapse rate of
I don't
the
disagree with
water
that part.
to the the few centimeters you are above the water, the lapse rate of that is a lot greater than it then being a bit higher. Because the lapse rate
Okay.
is higher, meaning you're going to get a higher coefficient of refraction, meaning that it can make it look concave. Did you get that? You cut out for a sec there.
Yeah, I'm gonna go to the I'm gonna turn the bandwidth down on the Google Hangout
Okay.
page. Outgoing. All right, here, I'll just turn that down. Maybe that'll help with us cutting in and out. Okay, I'm sorry. Go ahead.
That's okay. So, yeah, it's all to do with the coefficient of refraction. The amount the gradient changes over a distance. It's called the lapse rate, and the greater that lapse rate is compared to itself, the more the refraction will happen. So if you're closer to the water, it's really dense to relatively not as dense in a shorter
Right.
distance, meaning that the
Sure.
lapse rate is a lot higher, meaning that it will lift everything up higher, which will then even make it look concave if if that lapse rate is actually large enough.
Right, and that explanation does make sense on a convex Earth.
Yeah.
Well, in part, but that's with the assumption that more refraction allows us to see further.
But of course it does.
But what I'm saying is that it doesn't. What I'm saying is that my experience tells me that that argument makes sense if refraction allows us to see further. But what I'm saying is that refraction doesn't allow us to see further. Refraction reduces my visibility range. And you're right, it's because light's bending downward toward the more dense medium, and I'll show that. If you have upwards curvature like this, all right, let me see if I can. If you have, let's say you have upwards curvature like so, okay?
Yeah.
So if I'm seeing, let's say I have my line of sight like this, the more refraction there is, it's going to bend light downwards, okay? And it's going to reduce my visibility range because light's bending downwards. So where I would have been able to see way over here, because light's bending downward, it's reducing my visibility range. So now I can only see this far.
Well,
And when
yeah,
there's less refraction, I can see further and higher.
well, yeah, that's
So
if the Earth's concave.
what I
would make
noticed is that,
sense.
right. So on a convex Earth, if refraction allowed us to see further, then instead of our line of sight going off into outer space, because refraction knocks things downwards, now we're able to see over the curve, and we're able to see more distant objects over the convex curve. I understand that totally.
No, but you said knocks things down. It doesn't. It lifts them up. That's the point. The light is bending down, which means that the image you see appears to have been lifted up.
Appears to have been lifted up over the curve because our line of sight is bending downward over the curve, allowing us to see further over the curve. Yeah. If refraction actually allowed us to see further, but it's the opposite. That's what I'm saying. Refraction doesn't allow us to see further. I mean, refraction reduces my visibility range. And so
how did we see the Chicago skyline under those refractive conditions?
Because the refractive conditions weren't there. That was a very clear image. It wasn't very distorted.
No, refraction doesn't have to be distorted. That's the point. Refraction can literally just be the changing in the apparent position of what you're seeing. So the fact that you could only see the tops of those buildings shows that the image was lifted up slightly enough for you to see that.
Well, that not necessarily. That could just be atmospheric magnification, where it's going to be magnified. Therefore, you're going to lose the sides, you're going to lose the top, you're going to lose the bottom. You just only notice you lose the bottom because there's a waterline horizon.
No, because atmospheric magnification would be more of a constant.
Magnify everything.
We know the gradient of the atmosphere, and so the magnification over distance would always be kind of a constant, whereas the refractive condition based on the density change, the lapse rate, is what allows us to be able to see further. And if the Earth was flat or concave, then we'd be able to see that all the time. I mean, for me, it always reminds me of this moment playing Halo for the first time.
Even if
you got out of the ship, even if the Earth, and you could see it arcing into the distance.
Ring world.
Yeah, I mean, obviously it would be in three dimensions, but this is what you would see on a concave Earth.
No, because light is bending downwards, and your line of sight is being knocked downwards because of refraction, limiting your range of sight. See, you wouldn't be able to see this in a concave Earth.
If light does bend down, then the only thing that it would do on a sphere Earth is allow you to see further. It wouldn't limit your range of sight. It would change the apparent position of the horizon and the things beyond the horizon.
At short range, it would limit your sight. If your line of sight is curving more than if your line of sight is curving downwards due to refraction at a smaller radius or more than the curvature of Earth, then the more refraction you have, it's going to reduce if your line of sight is a smaller radius than the Earth. So it all depends at the rate of curvature of our line of sight.
Yeah.
That comes in because if the Earth has a certain curvature rate and our line of sight has a different curvature rate, if the curvature rate of our line of sight
curvature rate, I mean, let's just assume that our line of sight is straight.
Is bending downwards.
Let's assume that, like in this picture, our line of sight is straight, right? But what we're seeing has been lifted up by the fact that the light has bent down. So we're seeing further than we should, which is, it makes exact sense. And the fact that you can calculate the coefficient of refraction and the refractive index and everything, and apply it to things like Walter Bisland's curve calculator and even Mick West's more advanced one, and it models it out and it's always correct. The pure fact that light bends down is what allows us to see further because it's over the curve.
Right. what I'm saying, refractive, but the argument is that more refraction will allow you to see further.
Yeah.
But what I'm saying is that that's not true. The more refraction reduces my visibility, reduces, which would still be true on a convex Earth. This doesn't even have to do with the shape of the Earth, really, because this works in it. Because you're saying if your line of sight is straight and you have a curved Earth, then that means the more refraction would make your line of sight curve downwards like this. But you still have a line of sight that's a greater radius than the curvature of the Earth. If your line of sight were to bend so drastically that it would equal the radius of the Earth and then become smaller than the curve of the Earth.
Right.
Radius.
Okay. Right.
Then,
I see what you're saying.
At that
Yeah.
point, now the more refraction would reduce your visibility range, even on a convex.
But
so it all.
That's the thing. We can calculate the exact amount that light should bend based on the change in density over a certain height, and we know we can apply that to show that how much light could bend. There's no conditions where it would bend so much that it kind of comes back in on itself, and even at extreme refractive conditions where it's bent like that, you can still see further because all you have to do is look up and you'd be able to see more.
Yeah, I think that those formulas and those equations are, I think they have a faulty premise there.
No, they don't have to. I mean, we know that how much light bends based on the medium that it's going through, and if
but what is to say that that's a constant? Yeah, but how is that like if light is bending at this rate, what's to say that it's not bending down and bending back up off in the distance? Like, what's to prove that the curvature of light remains a constant?
Because
there's no proof of that either.
How much light bends based on the medium that it's going through, because it changes the relative speed of the light. And do you know what I mean when I say lapse rate? So because that's kind of an important point.
Why don't you explain it?
Right. So
okay, go ahead.
Lapse rate refers to the change in density of a medium over a distance. So if we were to go from water level to 1 meter up, and we were to say that the density changed by 15% over that 1 meter, that's the lapse rate. It's the amount of change in a distance, right? And if we know that, we know how much the light should bend. And that's why when you're doing observations, getting things like temperature and relative humidity at certain heights above the water is important, so that we can actually model it out based on the conditions that you're in. And there's a structure.
So there's already a structure set in place to determine, okay, if you have, and you can alter all these different settings. So it's already been predetermined. You see what I'm saying?
This is all based on our known physics.
None of it
light
actually
and
proves.
the mediums. If the density of the medium has changed by a certain amount, it means the light will have bent by this amount. I mean, it's literally just a mathematical representation of what happens when light enters a denser medium. And we know that when light enters a denser medium, it bends down.
That whole argument is based on a convex Earth. If
no,
you would actually,
not really.
If you could consider.
I mean, it's more to do with like Snell's law and stuff, which is, to do with the amount that light will refract based on the medium that it's going through. But who determined that?
How is any of this?
People tested the
proven
refractivity of different mediums.
But if one experiment is done in a different condition than another, how is anyone deducing? How is anyone
if you're
proving
always
for
measuring
sure
the density
how light
of the
is
medium,
then
you can always compare. I mean, people didn't just make it up and apply it to something. They tested under different conditions. Like
right.
I remember one thing I did at high school was you have a laser on like a tripod pointing down a bit of paper, and you mark where that laser is. Then you get a perspex bowl and an empty one and put it there, and you can see that just through the perspex, the light has shifted a little bit, and you mark where that is. Then you fill the bowl with water, and then you mark where the laser is hitting the paper, and it shows as the medium gets denser, the light is, brought towards you, is bent down, meaning that you should be able to see further if that surface is curved.
Right. All right. So I mean, we could probably go back and forth all day long about how light's bending and arguments in concave versus convex. I understand how it can work in both models, and so understanding how it can work in both models doesn't necessarily prove a model. So I mean, I guess maybe I'll take this conversation away from optics. Have you heard of the fishing line experiment? See, I'm wondering why
the torque the line, whatever they called it.
Yeah, torque the line was one attempt. It's not necessarily the concept is simple. It's not necessarily easy to accomplish, but I think it's the most valuable because for its difficulty, it's still pretty low cost and a pretty simple yet effective way to determine the actual shape of water. And we're talking about hard line measurements here, not like optics and all this other stuff.
The problem is the material to do that really doesn't exist. You need to have something that is capable of not having slack over those distances, and there is no truly rigid materials. So the problem you're going to face with something of that magnitude, where you're using a physical line under torque, under tension, to see if it can form a tangent to the sphere, isn't going to work, because there will never be a condition where that line doesn't have some slack in it.
Well, if you use fishing line as the same exact density of the water, then it shouldn't be buoyant and it shouldn't sink. In theory, if your fishing line's the same density as the water, it should just and you tighten it enough, if you can find that, which I believe was a problem. But my point is this: is that certainly these are things that, different plumb bob, like all these. This ties into your question earlier. Are all the space agencies lying? And I say yes. And that's that's just based on the footage that they provide us, the pictures and stuff. It just doesn't feel real. But aside from that,
okay, we'll get back to that.
I think even universities, aside from the space agencies, I think there should be more experiments. There should be more. There's plenty of people with money out there that could do these, more plumb bobs, or dare I say it, a rectilineator, which is really kind of tough and not really the most viable. But fishing line experiments, the plumb bob experiments, these are experiments that should be reproduced all over the shape of the Earth. And the absence of them doesn't prove a model, but it does raise a lot of questions. And so that's
okay. Well, my first response to that is that actual scientists and space agencies really don't care about proving anything. They're just working on the assumption that they're right, and they're going to do their science based on that. They don't want to do experiments to prove anything, because they're more interested in advancing humanity. And
I'll rephrase that. I'll rephrase that. Instead of saying these experiments haven't been done to prove anything, all right, I'll change that and say these experiments haven't been done to provide any evidence. Regardless of the shape, whether it's flat, convex, or concave, there could be more effort going into providing evidence that would add to our confidence.
But that's my point, is that they don't care about creating evidence, because as far as they're concerned, it's settled.
That's right.
Right. And they have to work off that. But
that's why
real world examples.
That's why I use the term faulty presuppositions. That's why I use those terms, is because
you say presuppositions.
Science isn't supposed to have anything settled.
It's not on presuppositions. It's on things that have been demonstrably demonstrated to be a fact. And they everything that they do is working on now advancing us to the next level of understanding. And I believe that they're all doing that, and they're trying really hard. And we're getting to the age of space travel, where it will be available for civilians this year. They're Blue Origin. I
Didn't
think, was
Virgin
sending
say
a
that
whole
like
thing.
15 years ago?
Yeah,
Virgin
but
was
it's,
supposed
it's
to have
actually
people.
happening this year, and they've sold
Right.
tickets to people, and
They sold tickets a decade ago.
No, not like this. Not with Jeff Bezos with his
Say
thing.
Virgin
They've
Atlantic sold
actually.
tickets.
This is very, very different. You need to look into what Blue Origins are actually doing with the civilian, and then they're putting
I'll
the
check it out.
civilian bit onto the International Space Station. They've got a space hotel. Manned missions to the moon and to Mars are planned. And you can't just keep saying these things in this way. It's never been at a stage before where NASA have been like, well, we're going back and it's going to be in 2024. I mean, that's NASA's goal. I think the US Congress have other plans, but they've never been at a stage where they're so set on the plans and saying the technology is now ready that we can do it. They can't then keep going with that lie and people still fall for it, right? So I honestly think that the whole thing is going to be settled in a few years when civilian spaceflight is a thing. And especially when you can go and book a flight for 200,000 and there's people like Flat Earth Millionaire out there who says that he's a millionaire. Well, why doesn't he go and drop that 200,000 that he's putting in a challenge for Globers? Why doesn't he just go and book a flight?
There's a few flat earthers out there that owe some money.
I
one thing I want to
anyway. But there was something you said that about. Oh no, never mind. It's gone.
Something I wanted to expand upon my claims of faulty presuppositions, and I'll provide some substance for that. Excuse me. What we're taught in school books is that Eratosthenes, with his sticks and shadows, proved the circumference and size of the Earth.
Eratosthenes, yeah.
Right, Eratosthenes. Tomato. Right. But this guy thought the sun was 3 million miles away, and Kepler thought it was 12. So we've got all these varying distances, and so Eratosthenes could not have been correct.
Well,
because
the thing about Eratosthenes
if he was off by,
he
only used. If he was off by 90 million miles,
yeah,
that's almost 30, like 300. That's
so much. Eratosthenes, he was.
So while he got the answer correct,
when he did his stick measurements, he was more looking at the shape of the Earth. He was just working on the assumption that the light rays were coming in parallel, and based on that, he could calculate the circumference of the Earth. Now, the thing about Eratosthenes is that
the light rays can't be coming in parallel. Otherwise, your lunar eclipse doesn't work. It
does. We'll get back to that.
Whoops.
But if this no, it really does. But if the sun is far away, be it 3 million or 93 million miles away, and at the size we say it is, or bigger than the Earth anyway, then the light rays will be practically parallel. And that was the assumption that Eratosthenes was working on, right? And using the two sticks, he managed to figure out roughly what the circumference is. But the thing is, it's been done a lot better recently. If we look...
But how is he able to determine the size of the Earth based on the shadows of the two sticks?
With trigonometry.
Right, which isn't going to work if his distance of the sun is incorrect.
No, again, the distance to the sun wasn't really.
So somebody's.
He was working on the assumption that the light rays were coming in parallel. That was all that he was. That was all he needed to know. And is if the light rays are coming in parallel, then based on the measurements that I've got, this should be the circumference of the Earth. And
but they can't be coming in parallel because we've already deduced that light bends toward the more dense medium, and since the sunlight is traveling through the air to get to his sticks and shadows, then that light cannot be parallel if we know it's bending.
But proven. Here's the thing, right? At what point did he do it during the day at solar noon? At the point when the light was directly above them, meaning that it's not coming in at an angle, meaning it's not going to refract. That's why he chose to do it at solar noon.
But if we know light is bending, then how are his lines parallel?
Again, it was
if the light rays
the light rays will only bend if they're traveling through, like sideways through a medium with a gradient, right? If it's going straight,
it doesn't have to be sideways.
Yeah, but that was the point about solar noon, the fact that the sun was directly overhead. That was the basis that they were using it on. That light was
At
parallel
zenith.
and that the light was overhead, right? Yeah, very good. Yes. So
Light doesn't bend at zenith.
that means that if the light is directly overhead, the light isn't going to bend because it's going directly through, parallel to the medium. So that was why he chose to do it at solar noon at both in Serene and the other place, right? And then based on those things, simple maths told him the shape of the Earth and the circumference of the Earth.
So you're saying he waited for the sun to be directly overhead at this location at one stick,
Yeah.
and then at the other location. But how did he do that at the same time?
Oh, he had other people at the other locations. He didn't do it at the same time. Solar noon is going to be different for each location, and he just needed someone to measure the angle at one place and measure the angle at the other place. He didn't have to personally do it.
At two different times.
Yeah. Well, at solar noon at each of the places. Obviously, depending on where you are on the globe, you're going to have a different solar noon.
Well, if it was solar noon in one location and you had the sun directly over the, it just.
But like I was saying, it's actually been done more recently, a lot better. I mean, Eratosthenes did it with two locations, but YouTuber called Slice Arcane did it with 23 participants in 9 different countries.
Okay.
Where's my screenshot? There it is.
If light rays are coming in parallel.
Yeah.
Okay.
Sorry, one sec.
So you understand in the concave Earth model, what you have above you is a more dense medium than the Earth, because while you have this quote unquote heaven above you, still the heavens above us, like consider an onion. You have all these different onion layers, if you will. What's above us? It's the heavens in the concave Earth model take up more volumetric data, and because they're like, I'm just saying in the concave Earth, and there's liquid up there. And there could be other phases of water that we don't have down here on Earth.
We're not talking about what the actual thing is. We're talking about the medium, meaning the atmosphere. And we all know that the further you go up, the thinner the atmosphere is, right?
The thinner the atmosphere. However, at a certain altitude, what if there's something up there that's very, very, very dense? And so I agree, based on the pressure gradient, I agree that within our airspace, within our living confines, within our air, obviously it's more dense as you descend. And, it's less dense as you ascend. There's less pressure. You got to bring oxygen tanks, all that stuff. I'm saying ultimately at a certain elevation, if there's something more dense, then ultimately light could be, because we're so low to the Earth, that within our own each human can only see a couple miles, right? Viewability range. Within our own viewability range, light is going to be bending downwards. But ultimately, our line of sight could be bending upwards off in the distance because of the more dense medium in the air. And so I don't think light is bending.
Be any point where you were looking through that.
What I'm saying is I don't think light is bending only down or only up. What I'm suggesting is that it's both. Depending on all these different things coming.
I mean, I can demonstrate to you with experiments how light bends when going through a medium. Have you got anything that could suggest what I'm suggesting about the nature of light is to be the case? Because all experimental evidence would point to the contrary.
The nature of light.
I mean, light doesn't just bend towards something that is more dense. It has to go through a medium with a gradient of density to bend. If it just goes from one density to the next, and that's a solid density, then you're just going to have like a straight angle of incidence, like in this, right? So that's just going from one density to another density, and you just see a straight line. But if that cube was to get more dense towards the bottom, the light would be curved. It's when it's going through a gradient.
I agree with you. All right, so we've all been to. All right, so picture you're in the summertime, right? And it's real humid out. It's real humid out, and you look over and you look over, say, a grill, and there's whatever. There's some vegetable kebabs on the grill, and you see all that waviness. You see all that distortion in the air. What I notice is that in real dry climates, when there's less humidity, the air is clear and you can see far. So it is true that light bends with a more dense medium, which means the more dense the air is at your viewing altitude, say, 5 foot 9 inches. That's where my eyeballs sit, right? So at 5 foot 9 inch altitude, I'm looking out, and down here, the air is very dense, which limits my vision. When in more humid conditions, where the air is more dense, my line of sight bends down more. So I agree, it's bending down. But when there's less distortion and I'm able to see further, when there's less distortion, less refraction, that's when I can see further. Everything looks concave. That what we're taught, the argument of refraction, is reversed. I'm not arguing
assuming that there's less refraction. When you're closer to the water, there is more refraction.
Right. When I'm closer to the water, what I'm saying is I always get close to the water.
Yeah, no.
I'm saying is
the videos.
I stopped with the tripod. It's just silly. It's because then your hallway and all this flat earth bullshit. All right, so excuse my French, but so I always get down to the water. Okay, so there's not a semantic argument about when I get down to the water and when I don't. I'm always going to be down 5 inches above the water surface. What I'm saying is that when the air is clear and the air is not as dense, I can see further.
But
we're taught the opposite.
No, but that's the thing. You agree that it's more dense closer to the water, meaning that it's going to bend down more. That's literally
right.
What's
What I'm saying is
further. And if the coefficient of refraction is high enough, it's going to make it appear concave. And that will literally happen the closer you are to the water when you get into the denser medium. And you have that lapse rate that's actually greater because the change in density over that is higher than if you go up a little bit more.
Forget altitude. Let's just assume that I'm always talking about 5 inch altitude. Okay, so yeah. I'll go there one day, and I'll zoom out and I'll be like, damn, I can't see the opposite shoreline because there's too much refraction. My line of sight is being bent downwards and not allowing me to see further because my line of sight is going like this. So everything looks like it's going over the curve. The next day, I'll go there.
You're just assuming you won't see the light that is going over the curve. I mean, there's still light that's going over the curve, so you're still going to see it. Not all light is going to do that because you're looking into the distance. So the further into the distance you are...
What I'm saying is that the over the curve is the faulty presupposition because it's likely that the Earth is curving upwards and that the more refraction you have, it reduces your visibility range, making objects appear lower and lower.
It's not going to reduce your visibility range. It's going to increase it because there is light that is going over the curve.
Right. Okay. Well, you see it as going over the curve, and I see it as going into the curve. Because in your objective reality, the water is curving downwards and away from you. And so light curving downwards is allowing you to see further. In my objective reality, water is bending upwards. And the refraction is bending my line of sight downwards, reducing my visibility range, making it look like those windmills are over the curve, off in the distance. See what I'm saying?
Yeah.
And so
what you're saying is the opposite of how light works.
No. What I'm explaining, I'm telling you what I see. What I'm saying is that I think what we're taught is the opposite because it doesn't match my observation.
What we're taught is correct because we know how light acts
I know
when
what
it
we're
goes
taught
into a
isn't
medium.
correct.
So
I already know. I already
mean-
know what we're taught is correct. I know that.
let's
I
get
can't.
back
I'm not
to
going to be able to prove
the
that in a
arguments
live stream.
about
I'm just saying.
space travel and stuff, right?
This adds to my confidence.
So, I mean, we're just going around in circles on the light thing. So, I mean,
Sure, that's. I mean, that's everyone's just going to have to, test that for themselves.
Yeah, I can demonstrate, and it has been demonstrated how light works, how light acts when going through a different medium. I mean, and that will allow us to see over the curve. But a lot of your argument lies with the fact that you think all the space agencies are lying to us. But I think, at what point are you saying that there is then this denser medium? How high up? Do we have a number?
I could throw a number out there, say the Kármán line, the ionosphere, 100 kilometers, 62 miles. When you look at the Operation Fishbowl, it seems like they exploded something against a ceiling. Regardless of shape, it does appear like there's a ceiling up there. It does appear that there's a barrier up there, whether you want to say it's glass or whatever.
But there's videos of rockets going from launch all the way up into past the Kármán line.
Yeah, I just don't have any faith in the altimeters, and I just don't have any faith. I've just learned to. So I've kind of just reset. So I'm kind of just starting over, and what I've come to realize over the past few years is that we're not being taught the truth, and they're gonna throw in a lot of truth in there to hide the lies, and so there's gonna be a lot of disinformation. That, for example, satellites. Flat earthers will say satellites aren't real. I used to think that myself. I do think satellites are real. I just don't think they're real as we're told according to the helios. I don't think there's satellites orbiting at 250 miles around the outside of a convex ball. I do believe there's satellites orbiting around inside the concave Earth.
Right. So how does gravity work on your model?
Well, first of all, I don't see gravity as a force. I see gravity as a label. I see gravity as a label used to describe an experience. So if I let an object go, why does it go downwards? The accepted answer is this force called gravity. I don't think there is a singular pulling force pulling everything down to the outside of a ball towards the center of the convex ball. Even if the Earth were a convex ball, I don't accept a singular pulling force because that can't explain why anything goes up. Why does anything go up if the only force is downwards? I would suggest that
quickly.
I would suggest
you understand more about our model, right? You say, how do things go up if there's a pulling force pulling everything down, right? So if you're talking about a helium balloon, right, it rises, okay? The reason it rises is because the mass of the air around it is greater than the helium balloon, right? There's more density, there's more mass, there's more for gravity to act on, meaning that it's pulled down around the thing with less for gravity to act on. And that will naturally create an opposite force and push it in the opposite direction. You have to have buoyancy.
Pressure.
So you have to, no, but it's the reason that pressure is caused is because of the vector of the air. Now, this is similar, right? If you have that,
but it's the air pressure pushing the balloon up.
But you're missing the point that pressure is caused because there is a vector to the air. The air is being pulled down, right? And it's similar to if you're in a car with a helium balloon, right? If you're in a car and you slam on your brakes, what happens to you? You get thrown forward, right? But if you have a helium balloon, you slam on your brakes, that helium balloon's actually going to go backwards. For the same reason that the heavier air has been moved around it because of the perceived force of the acceleration of you going forward.
Right.
So there has to be an acceleration in a particular direction for there to be buoyancy.
Right. I think the only way buoyancy can exist is if there's opposing forces. And because the helium balloon is less dense than the air around it, it's the air creating pressure, forcing the balloon upwards.
Yeah, but how does the air create pressure? That's the point.
Well,
the thing that
right.
creates the pressure is the gravitational vector on the air.
How do we even have pressure without a barrier?
Because not all things are like physical and physical forces.
I think
I can demonstrate to you right now gas pressure without a container. That's quite easy.
Okay.
Sorry, one sec.
See, I don't believe that mass attracts mass. I believe that it's the air, it's the ether attracting one mass to the other mass.
There definitely isn't
I don't
anything
think
called ether.
All right. Well, we can argue about that, but
Where's my?
I don't believe that two objects, each one has gravity, and the gravitational forces of each object are pulling each other together. I believe it's the air forcing the two objects together. So I don't. So the whole concept of gravity is the singular force pulling downwards to the center of the ball. I don't think that's the case. I think we live contained, and I think there's not just two. I think there's many forces, and all of these forces, whether it be electromagnetism, whether it be air pressure, whether it be dielectricity, all these etheric pressure, barometric, all these different forces coming into play total up to this experience that scientists 500 years ago, because they didn't have the tools we have today, they just called it gravity. And so that's why I call gravity a label, is because it's really just a label slapped onto the experience of all these combinations of different forces, all working intermingled together to equate to why we experience things going up and down. Nothing goes sideways.
That's the thing.
When we let something go.
If we look at Cavendish or Schehelian experiments, that shows us that the attraction isn't just up and down; it is sideways as well. But you
sideways,
were saying,
slightly.
Yeah, obviously depending.
Maybe 15 degrees per hour. Right?
No, that's different. The larger the mass, the larger the gravitational attraction. But you wanted to see gas pressure without a barrier. I mean, what I'm about to show you is the inside of a nuclear reactor. Okay, a nuclear fusion reactor. Inside these reactors, they are 10 to the negative 11 torr, right? So it's a practical vacuum. And they inject some ionized gas into it, and then they run an extremely high voltage around the bit in the middle. And what that does is it draws all the gas into that one band, the blue band that you see, right?
It's the blue ring?
Yeah. So that band of blue is pressurized ionized gas. Anything outside of that is 10 to the negative 11 torr. And what you see
That's why it's blue, like our sky.
Well, no, the blue is actually the effect of a nitrogen impurity that they put in there so that you could see it better. Normally, I think it's hydrogen or helium plasma, but what that shows is that there's an apparent force, like an apparent barrier around that, okay? And we can calculate what that force is, but there isn't actually a force on it. What there is there's an extremely high electrical current being run through it, which makes the electrons rearrange themselves in such a way that it pulls the atoms towards them. If you can run a high enough voltage through it, a high enough current, it pulls the atoms so close together that you have something called a theta pinch, which is the start of a nuclear fusion reaction, which you see here. The stronger and stronger current, it gets more and more contained, but they get to a point where they can't contain it, and the atoms overcome the nuclear forces, and you have the start of a nuclear fusion reaction, which you'll see here. So that was, yeah. So that was the point where the atoms were pulled so close together that it overcame the nuclear forces and started nuclear fusion. But what that shows is that you don't have to have a physical barrier to have a container. A container can be a pseudo force which I refer to as an emergent force, a consequence of something else. In that case, the consequence was a force seemed to be there based on the amount of current that was running through. With gravity, the
It held
emergent
all the
force.
gas in a certain. It held
Yeah.
all the gas in a. It was the simple energy that held all the gas in a
Yeah.
specific location
And it's the
without a
same with
tangible
gravity,
barrier.
right? Gravity is an emergent force. It's a consequence of the curvature of space-time. And that applies an energy barrier to the Earth. Any molecules of air have to have enough energy to overcome the gravitational energy to be able to get out. If they have enough kinetic energy, they can go up high enough and then escape the gravitational attraction, which happens quite a lot. We lose quite a lot of atmosphere to space all the time, but
How does any of that not work in the concave Earth? Because
because
couldn't all this still
we
be
can
true inside of a sphere
we know that
where
gravity
you just
acts
have it
in
inverted
that we
and you instead of having all this water sticking to the outside of the ball, couldn't it also work where you have a downward instead of an outwards
nah, and that's the
water,
thing, right?
a downward
We
force?
know that
Couldn't you have a
gravity
downward pushing?
we know that gravity always acts towards a vector, right? And you can have two plumb bobs at a certain
Downward.
distance apart, and the
Yeah.
top of the plumb bobs will be further apart than the bottom of the plumb bobs. There is actually bridges that are built with the towers. The tops are further apart than the bottom, but relative to their own gravitational vector, they are completely level, and that shows that there is a concavity to the Earth, and a convexity to the Earth, and not a concavity.
Well, there's actually mixed results on that. So I don't even like using the plumb bob or the rectilinear for those reasons because they're buried in time and buried in history.
Hey, you there? Right, can you hear me?
Yeah, I can hear
Right.
you.
Okay. Sorry about that. My software completely just crashed.
Oh,
Give me
okay, no
one
problem.
sec, and we will get back online.
Cool.
Put my string key back in. We should be back live now.
I'm in the Hangouts page. Our call is still open. That's all right.
Okay.
I'll screen share after if we need to.
Right. Okay. That's better. We're back.
All right. So where were we? We were talking about the rectilineators. It's a concept is brilliant, and it's the same concept as the fishing line. However, they are different.
So I'm trying to remember what I was gonna reference that to. All right. Yeah. So there is, like I said, there's bridges that have been built where the tops are further away than the bottom. So how does that work if the Earth's concave?
I'm sorry. What did you say that again?
There's
Sorry,
there's bridges where
you
the
know,
towers of the bridges, the tops are further apart than the bottom, but the towers themselves are perfectly level. How does that work?
Then you have a bridge where you have vertical beams where the top is diverged from the bottom.
Yeah,
And you're saying how do you have a level surface? You could still have beams that are
but the bridges are the towers of the bridges are built so they're like with a plumb bob. They're perfectly level, horizontal to the earth. Yet the tops of the bridges are further away than the bottoms of the bridges.
could you source an example of that?
I'm just trying to.
Because that would be good evidence for convexity.
All right, the Vera Nazo Narrows Bridge. Sorry, one sec. I'll just get the page up.
All right, I gotta
Right,
go back and mute this.
The Vera Nazo Narrows Bridge. The towers are not parallel to each other, but are
Verrazano
1/5/8.
Bridge?
Yeah, 1/5/8 inches further apart at their tops than at their bases.
1.5 inches.
Yeah, and that matches the distance that they are apart.
The Verrazano Bridge. Isn't that somewhere on the East Coast somewhere?
In Upper New York Bay.
Yeah. Okay. So they measured the top and found that it was 1 inch and a half greater than the bottom.
Yeah, yeah.
I'm not so sure. I
They're
mean,
1 5/8 inches further apart at the tops than at the bottoms of those towers.
now what do they use to measure that? Because that seems kind of negligible. I mean, when you're constructing large construction project like that, 1.5 inches is
Yeah, but they know that the towers
that
are
could
exactly horizontal.
that could either be a construction issue or a measurement issue. I mean, why would they have needed?
I advise you look into it because it's not the only
Okay.
bridge in the world that has that feature about it. That the tops are
If
further
all
apart than the
bridges
bottom.
are consistently reporting divergence to their vertical beams, then that would evidence of convexity.
Yeah, so the tops are further apart than the bottoms, meaning that if they are plumb, then
divergence.
that works. Right, okay, so we were talking about space, and... Oh, no. Are you there?
Up here.
Right, sorry, you cut out for a second there. So, right, you were talking about space, and we were saying that there's a certain point where it gets more dense, and you're saying that's at the Kármán line, but we have evidence of rockets going into a practical vacuum.
Right.
So how is that the case?
I've seen enough And I'm not saying that everything is fake, but I've seen enough fake stuff where I just don't trust what I'm being presented. Especially nowadays, where in today's world where you have all this technology and seeding, nowadays, even the average everyday person could make something look real on the screen. And so just because I'm skeptical doesn't necessarily prove they're lying. What shows me that the spaces are lying is that's obviously not real. What we've all seen those CGI globes. If they were able to go
what are you
in
saying
the outer
is CGI globes?
Well, you see that thing rotating behind you.
Yeah,
It's a generated image. It's not a photograph.
no,
And so
that was created to be CGI.
Right.
There's plenty that is real, and even in real time.
But why? I mean, if it's easily attainable to take photographs of the spherical Earth out in a heliocentric fast outer space, I just don't see why composites are even necessary, or ribbons of imagery. None of that stuff should be necessary. It's almost like
that's to do with the size of the Earth.
It's almost asking flat earthers why spherical projections of the Earth exist. If paper and Earth are already flat, then three-dimensional spherical projections would need to exist. So, but by that same very logic, where I can fight against flat Earth with you.
Yeah, but you said why do they need composites
that same very
and stuff?
logic?
Let me respond to that. Right.
Okay.
If you're talking about like high quality images of the Earth, okay, the Earth is massive, and even if a satellite is orbiting in low Earth orbit, it's still relatively close to the surface, so it can't take an image of the whole thing. So
but the Hubble should be able to do that. The Hubble should have hundreds and hundreds of photographs of the Earth.
But the Hubble is not doing that.
Fact.
The Hubble is looking out in space.
Of course, the Hubble has never done that.
Yeah, but
that's the problem.
That's a bit of a straw man, because the Hubble was never designed for that. It's literally,
what do you mean it was
not
never
the purpose of it. It's designed to look into space, right? But if you want to know why there is composites, it's because if we want high quality images of Earth, then we have to have something close enough to get those high quality images. And because Earth is massive, it needs to do it in multiple bands. But there is lots and lots of images and videos, even real time, of the entire Earth. They're not going to be as high quality because they're not as close. But there is lots that Echo Star 11 was a 24-hour live stream of Earth for years. Himawari, there's so much that is like real time that is there available to see.
I've looked at a lot of that ISS footage, and I'm sorry. It's just when it's nighttime. First of all, there's problems with that ISS footage, because you'll see consistent footage, and the time elapsed in the footage shows that they should have traversed the entire spherical Earth, but it was daytime the entire time. The ISS footage should have shown the ISS passing through nighttime, and it doesn't a lot of times. But aside from that, you can tell that a lot of that, like that's footage of like nighttime, and you see all these different like lights lit up and all these different. That's clearly fake. It's clearly not.
You
I mean,
keep saying
cities
it's clearly
wouldn't be
fake,
lit
right?
up like that.
For you to say it's clearly fake, you must be pretty good at discerning what is real and what is fake. Is that fair?
Yes.
All right. Should we play a little game?
Hey, I want you to check out a video called. It's actually a Mark Sargent video, believe it or not. It's called "SpaceX is Real. Don't Research Flat Earth." And when you see that video, it's a pretty good one. You see all the fireballs and stuff, but you can see how anything can be made to look real. So obviously, 5 rockets didn't launch up into the sky simultaneously. That would have been news all across the globe, right? So, so obviously that didn't happen, but it looks like it.
So for you to be able to say that, you have to think you're pretty good at discerning reality from fiction, right? So let's just go. I think there's 10 photos in here, and I'm going to ask you if you think they're fake or a photo. All right?
If I fail this, it proves my point. If I fail this, it proves that it's hard to determine real from fake.
But you just said you're
You
really
understand
good.
that, right?
No, you just said you're really good at determining what is real
Right.
and what is fake.
Right.
And for
Even
you to
someone
be able
really
to
good.
say, well, that's definitely fake. That looks fake. Then you have to be good at discerning what is real and what is fake. So let's test that. Is this a CGI or is this a photo?
I don't know.
Take a guess. Based on your...
That could easily... Everything you show me, I'm going to say I don't know, because I understand that anything real could look fake, anything fake could look real.
Well, then how can you say that the how can you, if you're taking that stance, how can you say that the ISS footage looks so fake?
All right. Well, if I showed you a video clip from Grand Theft Auto, would you actually look at me and say that's real? No, you know it's fake because it's obviously computer generated. I know when I'm looking at a computer generated image, like the rotating sphere behind me.
Yeah, you're saying that.
I do. So
but you're contradicting yourself there, because you're saying I know if I'm looking at a CGI image, but if I show you a picture and ask you to tell me if that is CGI or real, you're saying I don't know because everything can look real.
It's because yeah, something fake can look real, but something real can't look fake.
Yes, it can.
So that if I show you something that's obviously fake, you know it's fake.
Well,
if I show you Bart Simpson doesn't really exist. It's a cartoon, so that's obviously fake.
I've seen him on TV.
So if I show you a picture of Bart Simpson, that's obviously not a real person. You know that's a cartoon.
Yeah.
So when I look at a cartoon,
you can look at
I know it's a cartoon.
ISS footage and know that that's fake. But to know that, you have to be good at discerning what is real and what isn't. And you can't then say, well, everything can look real.
No, you don't.
I don't look at the ISS footage and think it looks fake. I understand the physics of how things should look.
You can look if you look at something that looks real, it could be real or fake. But if you're looking at something that's obviously fake, then it's obviously not real. So it's not.
What do you think, like mirages and stuff are in the desert? You know, optical illusions that can look real, and but I mean, you're kind of defeating your own argument there.
Okay,
you're saying, I
so
can't tell real from fake, but I know that's definitely fake. It doesn't make sense.
All right, so can I screen? All right, here's a good time to.
You there?
All right. So here, I'm going to screen share this real quick. I'm just going to go. I'm just going to look at some images. All right. I just want to find. Let me see if I can find something here.
And also, while you're looking, you said that there's videos of ISS for the entire orbit where they're in day. Could you show me where I can find that video? That'd be 93 minutes of it being consistently day.
Well, if you go to, you can look on YouTube where it shows like the ISS live streams, and you're seeing the Earth like zip by, and it's daylight the whole time.
Yeah, have you sat there
I don't need to source.
Have you sat there and watched it for 93 minutes? That's how long an orbit takes.
Well, you could sit. Well, if you're not able to look at an entire 93 minutes, it's because it's cut. So I don't think you can look at an entire 93. If you watch for 93 minutes, you're either going to see a cut or you're going to see daytime the whole time. I'm sorry, I'm just trying to find.
That's okay. You kind of debunked yourself.
Pictures of a globe. I'm sorry.
Sorry, you again, you kind of contradicted yourself, like by saying that, well, you can't really see a 93-minute one, but you also said there is one where it's daytime the whole time.
What I'm saying is they're always showing you daytime. When they're showing you nighttime, if you try to watch 93 minutes, you won't be able to because they have cuts.
Yeah, a lot of the time they're outside of communications range.
How is that possible if there's satellites all around this outside of the sphere?
Not all satellites are designed for communications.
Then what the hell? Then what are they doing up there? If they're not communicating, why have them up there? Anyways, I'm sorry. I'm looking for. We ought to know what those are since our taxes are paying for them.
Well,
so anyway,
with NASA,
I don't need to. Okay, so I don't need to show you. I'm not going to bother screenshot. I can't find it right now. Anyway,
right,
I don't need to show you all. Flat Earthers have shown you all the CGI globes already.
Okay.
So you've seen all the. It's no. I mean, we've heard of.
I don't think NASA have ever shown us a CGI globe unless they've said that this is actually CGI.
Of course, if you look into the Simmons guy, he's the one who actually creates them, and he says that they're created, and they use bands of image, and it's probably
that doesn't mean it's CGI. They can't
go high enough
things together.
It's exactly CGI because they have to copy and paste the clouds in after.
He was only talking about one picture, the 2012 Blue Marble, I think it was. And his point was that because of the way the data was gathered, it had to be put together in a program. But not all
because
photos are like that, and that doesn't mean that's CGI. That just means it's a composite, and most photos are composites anyway.
Okay, well, we could get into semantics. If you want to say that composite doesn't equal CGI, I'm saying that composite does equal CGI. It's not a snapped photograph. It's bands of imagery that have been spliced together, and then they added in the clouds after, which means it's not a photograph. And if it's not a photograph, my question is why? Why do we need bands of imagery if we have satellites and the ISS and the Hubble? If we've got all this stuff up in outer space.
That particular picture was designed to be a high-quality image of Earth that looked nice. But you are assuming that there aren't any full images of the Earth. There is plenty of full images of the Earth. And that Rob Simmons guy doing that isn't trying to hide something.
But they're not photos. They're but images are not photographs. Images can be composites, CGI generation.
I mean, but if you take a photograph with your cell phone, that image that you get from your cell phone is a composite. It's the camera's RGB putting stuff together and then showing you that image. Most photographs are composites of some kind. Unless you're like
they're not altered composites. They're not bands of imagery that need to be spliced together and then the clouds added in after because they can't get enough altitude to just photograph the Earth.
Well,
you see what I'm saying? There should there
is plenty that are full images. But the point of that image that Rob Simmons put together was that it had to look in that particular way. They designed it to do that, and they weren't trying to hide anything. They wanted to get a really high quality image of Earth, and then they put it. That was the way they had to put it together. Why can't they get a high quality? Because you can't have that high of a quality if the camera is further away.
Well, how do we get all these amazing photographs of the universe from Hubble with such high clarity, but we get photographs of Earth with that clarity?
Because the images of the universe that we're getting are relative distance to the pixel size. If you were to actually zoom in really close to those things, based on that photo, it would be blurry as hell.
So you're telling me they were able?
So big.
So they created this. So you're saying they created the Hubble specifically to view those distances, but they won't create a Hubble to photograph the Earth at its specific distance.
They don't need to.
Why? To prove. Yes, they do.
They don't need to prove anything because they don't care.
Because there's billions of people saying, "Hey, all these globes are CGI. Where's all the real photographs?" They do need. That's our.
But there is plenty of real photographs. That's what you're saying. You're assuming there isn't any. But there's loads.
No, I'm not. Listen, but there's not real photographs. There's not loads.
But there is.
That's just not.
But there just is. Oh. I can show you loads.
Well, you can show us, but NASA can't. NASA has got to give us composites.
But you're talking about that one image that Rob Simmons put together in that particular way.
I'm not talking about one image. I'm talking about the 1972. I'm talking about
1972 Blue Marble was a single image.
What about the one that everybody sees on their iPhone? Sorry? What about the one that everybody sees on their iPhone? The one that everyone sees on their iPhone?
I don't
can't tell me that's a real photo.
What you're on about.
Me neither. I have Androids too. But if you look at this, all right.
But
Maybe I should just.
if you're talking about
it.
the 1972 one, that was literally taken with a Hasselblad hard camera with an 80mm film that was developed in a dark room. You know, there was no trickery, no
and how did the astronaut get perfect frames? Of, he wasn't able to look through the viewfinder, yet he was still able to get perfectly centered photos. It just here we go. All right,
tried.
So I'm going to screen share again, if you don't mind, because I found the image that I was looking for.
We've got about 5 more minutes. I need to read out super chats and then get ready.
All right, that's cool.
Produce for Reds.
Okay, that's fine. All right, so hide
screen.
Okay, so this image here. Can you see this?
Yes. What about it? I mean, different cameras, different imaging techniques, different distances.
So
different.
They're all perfectly. Number one, they're all perfectly spherical. None of them are oblate spheroids or pear-shaped. Number two.
Wait. Let's get
the
number
sizes
one.
of
Let's
the
do number one
continents.
first. Let's do number one first. That obliqueness is so small you wouldn't see it in the amount of pixels on the screen.
Okay, fine, fair enough.
The oblateness is 0.42% difference in the equatorial and polar diameters. You would not see that difference in the pixels on the screen.
And I agree, which means Neil deGrasse should not be calling it pear-shaped.
I've got a lot of issues with the way Neil deGrasse Tyson words things. Don't worry.
Okay, all right. So we agree on that. So, I mean, even the sizes of the continents here are different. You've heard all these arguments before from flat earthers. Now,
yeah.
I don't need to be a flat earther to understand that these are computer-generated images.
They're not, though. They're
okay,
all
well,
we've got
we could just agree
to
we could just agree to disagree on that one. Everyone can just make up their own mind. I'm not going to argue with you about it. You say they're real photos. I think they're computer generated.
I'm pretty sure that was taken Apollo 15.
There's no point in us arguing.
The 2015 one is Discover. The 1997 one is the MWAR satellite. I mean, they're all different. Like, if you have different lenses that create pictures in different ways, you're going to get different looking images. And if you are a different distance away from a sphere, then you will be able to see more or less of the sphere. The 2012 one, that was actually a lot closer than, say, the 1997 one, because the 1997 one was able to see more because it was further away. And I've demonstrated that in one of my videos, that if you are closer to something, you can see less of a sphere.
I think that the two bottom right-hand corner ones, the 2012 and the 2002, if you look at the 2012, the size of North America, I mean, the spheres are the same size.
Yeah, but it was closer to the sphere. If the angular size has been made the same for these pictures, right? But if one was closer, you're going to
the angular size
less.
of the continent should shrink as well.
No. If one camera was closer to the Earth than the other, it's going to be able to see less or more of the sphere. Right? Do you understand that? Like, and like I said, I've actually demonstrated that in one of my videos that I took a photograph, and so is Slyman Dan, Conspiracy Cats. If you get a normal sphere, a normal globe, and take a photograph really close to it of North America and then one further away, the one closer up will make North America look bigger because the camera is able to see less of the sphere. If you're further away, you see more of the sphere, therefore the countries look smaller relatively.
Okay. All right. Regardless of that, to me, these are, I mean, even if that's all true, these are clearly to me, and it's okay.
I disagree completely, and like that's why I wanted to show you the go through the game with you of fake or photo, because you're going, those are clearly fake, But if you can't tell the difference between fake or photo, where does your expertise in saying something
But
looks fake
but
come
I
from?
but I can tell. I mean, those are clearly not to me. I mean, you can. I mean, remember when like the internet came out like 20 years ago, and you had like remember that skiing game, and you you had to like click right and click left. I mean, like at a
Yeah.
very simple level, like you can tell Mario's not real. You can tell Sonic the Hedgehog isn't real. You know what I mean? Like all
Yeah,
these different things you
those
can
look
tell.
like real photographs taken with the equipment that is described.
I mean, Sonic the Hedgehog has never looked like a photograph. Sonic the Hedgehog has always looked like CGI to me. Same thing with Mario, and the
Yeah,
same thing with
but
these pictures of the Earth. They just,
that's not equivalent to that photo you were showing me because none of those look
I mean,
cartoons to me. They look like photographs, and the thing is,
and that's fine.
there's actually a channel that has demonstrated with the same type of lenses that you will get those effects. But anyway, I do need to start wrapping up now.
Sure.
So I'd like to actually pick this up at another time because there's some stuff that you won't get to, so we can arrange that for another time to carry on the conversation. Would you just like a couple of minutes? Any final thoughts?
Yeah, I encourage people to get out there and test things for themselves. Get your own zoom camera, zoom across the water, see if the refraction argument is true. Get out there, look at different pieces of evidence, things like spherical excess, the LIGO experiment that may actually lead to convexity rather than concavity. I also want to talk about the sun. No, that's something we didn't. There's a lot of things. It's a vast world. So there's a lot of things we didn't get into. We can get into next time. But the sun really sheds light. Trying to determine the position or altitude of the sun really sheds light on the situation. That adds to my confidence that we're not being told the truth. Is when you try to ascertain the altitude or position of the sun. And so these are all different things we can do to try to better our own understanding. And at the end of the day, if we end up being wrong things, that's great because that's real science and that's real honesty and that's real progress. And the more things we're wrong about, the closer we get to the truth. Someone who's right all the time probably never has the truth. So I encourage everybody. I hope we were able to learn from this convexers, concavers, flat earthers. I hope we all learned from this, and I hope we can do it again.
Cool. Well, thank you for having a civil conversation. I do appreciate it. Just like to remind everyone that the previous concave earther that was spoken to on my channel, Lord Stephen Christ Mercury, is no longer a concave earther. Deleted his channel and spoke to me earlier and said that he denounces Lord Stephen Christ. So that's good news in my eyes, and I just wanted to shout him out. And I'm going to read my super chats now. You're welcome to hang around while I read the super chats. Some of them can usually be quite nasty towards the guests, so thick skin may be required.
Definitely.
Saying Andreas for 10 runs. Dude, I'm begging you to do these earlier. I tried to do a different range of times, Lucien. I've got an early one tomorrow and an early one on Monday. So, Spike Smith for $2. What is the guest education level, professional qualifications? Do you what's your educational levels?
I graduated high school.
Okay, good enough. That's better than most flat earthers. Jerry Nassau, $1.99 for a sticker. Thank you. Cleaner Ben for £5. If you drink enough, everything becomes concave. Yes, I can agree with that. Jonathan L for $5 Australian. What technologies and knowledge can be developed for the advancement of man in your model that the globe model can't?
Is that a question to me? I don't know.
Yeah.
I don't know what. I mean, I don't really. I mean, the science is science, regardless of the shape. I don't know what model. How has convex Earth? What has NASA done with all our money? What have they given us? It's just kind of like a fundamental flaw in the question.
Do you
kind
know
of like
that
a loaded
every
question
single cent of NASA's budget can be traced?
$59 million, and they got to give us bands of imagery and CGI Mars. Like,
Yeah, but like I said, do you know that every single every single cent of NASA's budget can be traced? Like, on their website, you can go and see exactly what all the money is spent on.
Right.
I mean, they've got
And
a
we
whole
still have
bunch of
nothing to show
buildings
for it.
there.
What have they given us? They've given...
Okay, right, quickly, let me just...
they still have to run underwater cables, and the satellites aren't used for communication. So where's all our... I mean,
NASA
you said
are
yourself,
people
not
that
every satellite.
Not the things in there. Okay.
So what are the
20
satellites
things
doing
that
if they're not
NASA have given us. Camera phones, scratch-resistant lenses, CAT scans, LEDs, landmine removal, athletic shoes, life-saving foil blankets, water purification systems, dust busters, air thermometers, home installation, the jaws of life that firefighters use to break open cars from stuff, wireless headsets, memory foam, freeze-dried food, adjustable smoke detectors, baby formula, artificial limbs, computer mouses, and portable computers. All recent inventions by NASA.
What do any of those have to do with outer? Those could have all been. Those are all practical inventions that could have been invented by anybody.
But they were invented by NASA.
They have nothing to do with outer space.
Invented to make life easier in space, and then
but none of it has
to
to
make
do with
life easier on Earth. But you say where does the
none
money
of it
go?
proves the
But
model.
there's some of where the money goes. Inventing. I mean, we wouldn't be talking right now with about some of those inventions.
But none of that proves that outer space is real. Or that
It doesn't
Earth is a
need
ball.
to, but it kind of defeats the
Henry
argument of
Ford
where does that money
invented.
go.
But
When
Henry
there's things
Henry
that are
Ford
used
invented the
every day.
Model T. But Henry Ford invented the Model T, so the Earth must be concave because NASA created some Tupperware and some scratch-resistant lenses.
We weren't
debating whether
NASA were real. You were saying where does the money go? Well, there's 20 of the list of 60 things that NASA have invented.
Right, to convince. Okay, but why are they doing that stuff?
Because
why are they
these
inventing
things were
Tupperware
invented to make life easier in space.
But none of them actually prove that space is real. But we need freeze-dried food regardless of space.
What it shows is
scratch-resistant lenses don't prove outer space.
I'm not saying it does, but NASA invented these things to make their lives easier in space, and then they were
But when are they going to make?
for everyday
life. But when are they going to make our lives easier here on Earth? Because we're paying a lot of money, and they need.
Okay, so long-term goals is for NASA to mine the solar
Nikon
system.
could have made scratch-resistant lenses.
If NASA were to
we
mine
don't
the
need
solar
NASA
system and give us a bunch of resources that we can use, that's going to help us in the long run. But first of all, we need to figure out how to... There's a lot more than just petrified rock in space. But
resources?
From just one asteroid, we could get more precious metals than exist on Earth.
How much ice can we get from the mega cryometeors?
At first, we need to figure out how to do stuff in space. Mega cryometer was something I wanted to cover, and we'll get to that next time. But anyway,
how did the helmet fill up with water if outer space is not water? If outer space is a vacuum, how did that astronaut?
They have internal cooling systems and
but they don't have enough. But they don't have the internal cooling systems. Don't have enough water in the helmet.
Anyway, Jonathan L for $2 says, "How does gravity work in your model?"
Well, we went over that earlier.
It's the ether, didn't you? Yeah, we can get into next time.
Well, it's a combination. It's not any one thing. It's a combination of things, and I just don't think that a singular downward. I just don't think there's one singular downwards force. I think that's ridiculous. I think it's obviously a combination of forces.
Well, there is a vector sum of all forces. On Earth, you have to take into account centrifugal acceleration as well as gravitational acceleration. Schrodinger's cat for $1.99 says, "Nice guy, but stupid or Poe." I don't know. I think he genuinely believes what he believes. Fargoth92 for $2. What other forces do you think is putting down? We went into that. Ether and density and buoyancy and stuff. Rocket Scientist for $5 Canadian.
No, density and buoyancy are not forces. Nope, sorry, time out. I'm not a flat earther.
Buoyancy.
Density and buoyancy.
Buoyancy.
No, it's not. Buoyancy is a result. Buoyancy is not a force. Buoyancy is a result of forces. Buoyancy exists because of competing
buoyancy
forces.
is an opposite acceleration.
Buoyancy
needs a force.
Buoyancy. If you put a soccer ball underwater, it's going to be buoyant because there's pressure.
Yeah,
the pressure is
what
the
you
force.
can measure
Buoyancy
is an apparent force pushing it up.
Buoyancy is an observation. Buoyancy is the result of forces. Buoyancy is not a force. That's like saying density is a force. Density is a property. Density is not a force.
Density is a scalar. Buoyancy has a vector, therefore it's an acceleration. But we can get into that all later at the next time. Rocket scientist for $5 For fuck's sake, you keep saying I think. What have you demonstrated here is your total lack of understanding of basic physics. Fargoth92 for $5. He can tell what is real and fake, but can only claim he doesn't know because it could look real. Right. With JM on our hands. We're gonna save JM. Don't worry. Concave.
So I got a question. How come the ethanol on a spirit level is concave if it's under pressure? How come it doesn't convex? How come we aren't using convex ethanol on the spirit level to determine?
There's an air bubble in there.
Oh my God.
Yes, that is under the influence of gravity.
You mean pressure?
I mean gravity. Okay, we can also get into
there's
how
air
levels
pressure.
Work. Copernicus Thinker for $2. Concave, will E.T. Billu make a cameo appearance? Spike Smith for $2. Make him prove his expertise on the CGI test. No, he just said he couldn't. Copernicus Thinker for $6. Give him your usual fake or real series of photo tests. Well, I tried to. Gravity Axe for $5 Australian. You can't tell what is real, you just believe what some cult website tells you. Rennie Baby for $5. I'm going to need this guy to do the CGI quiz and do real research that isn't looking for YouTube videos and listening to idiots. Find smart people. Don't worry, we can have him back. I can help him. Philip A.
Yeah, well, I've got a...
Sorry, go on.
No, that's okay. I'm having fun listening.
Phillips A for $5. Panoramic photos are all composites, but that does not make them fake. Earth photos are basically panoramic photos. Yeah, I tried to explain it's to do with scale. Copernicus Thinker for $2. He's not serious, just mentally masturbating online. I disagree. I think we can help him. And John Rapp. Everyone say hi to John Rapp in the correct way. For $2 Australian. Zenith Atlas, you really are ignorant of science. And God's Auditor for $2. Sorry, Zeniff, take a college level physics class. You could do. You graduated high school. Just take a physics class. It might help.
Sure, I think it would help everybody.
Yeah.
Yeah.
I want to go back to college. I've been watching Community on Amazon though. It looks fun. But anyway, that's going to be us for tonight, guys. Zenith Atlas, thank you for coming on. I do want to get you back to go over some of the more nuanced things that we were talking about. Thank you for the decent conversation. It's nice for a change. In half an hour time, guys, I will be producing a debate on Red's Rhetoric's channel between Astronomy Live and somebody who thinks that that space is fake. So see you over at Red's channel in half an hour. But for now, guys, remember, stupidity is not a right. Fight the flat earth. Fight the flat. Fight the flat. Fight the flat.